Keynote, and it's my real great honor to introduce Professor Jason Cong from UCLA for the first keynote. And Professor Cong needs really no introduction. He has been a real thought leader for this community for many years. He is the Volgano Chair for Engineering Excellence Professor at UCLA, and he had a really illustrious career with close to 500 publications, including 16 Best Paper Awards and 3 10-year Most Influential Paper Awards. Many of you have probably used one of his tools because he co-founded AutoESL and Falcon Computing Solutions for high-level synthesis, and both of these tools have been acquired by, both of these companies have been acquired by Xilinx. He's a fellow of IEEE, fellow of ACM, and a member of the National Academy of Engineering. This year, he was the recipient of the IEEE Robert Noyce Medal for fundamental contributions to electronic design automation and FPGA design methods. We are very fortunate that he's going to share with us his vision on democratizing IC design and customized computing. So please welcome Professor Cong.
Thank you so much. Thank you so much, Professor Mitra, for the kind introduction. It's so good to see so many of you here and in person, and it's wonderful we are sort of back in business. And let's just wait for this the screen to show up. It's my distinct honor to be here to give the keynote on this opening day. ICCAD is always very special and very important for me for a reason. Is that my very first paper was published in ICCAD 35 years ago. On this slide, you'll see on the left-hand side is the first page of the paper. In fact, I couldn't find the electronic copy of the ICCAD proceeding, but was able to find the journal version of this paper in TCAD, the transaction on CAD. On the right-hand side, you can see 4 young graduate students from University of Illinois, and I was one of them. And the person standing next to me is Professor Martin Wang. Now he's the Dean of the Chinese University in Hong Kong. The young lady there is now with IBM Poughkeepsie EDA group for many, many years. And the gentleman on the right is the Casey Chen. Some of you may know is many years ago, he co-founded Verplex, a very successful verification company being acquired by Cadence. So it's bring up a lot of memories when I search for this photo. And more importantly, I will say that I like to dedicate this talk to my PhD advisor, Professor C.L. Liu. He's a senior author on this paper. They really taught me how to do research and guided me into the EDA. I very much wish that he could be here with us today. That unfortunately he passed away almost exactly 2 years ago. But I think all of us owe him a lot for his decades of contribution to this field. So the paper is actually about a new approach to 3-layer channel routing. Why is a new approach? Because paper was written in 1987. At that time, there's only 2-layer metals. And so we speculate saying that the industry is going to move forward to have 3-layer metals, and how do you do routing then? Indeed, two years later, if you see at the bottom, 1989, Intel indeed introduced the 3-layer metals in their 486 microprocessors. 486 also reached another milestone, the first one over 1 million transistors. So that was the excitement we had. Fast forward, so where are we today? That 35 years later, if you look at for example, one example, this Intel 4 technology, also known to be the 7-nanometer process technology. This is with the EUV, and it actually has 17 layers of metals and on the left-hand side. So the design complexity has increased dramatically over the years. So if you look at the research program and of my lab, I will say during these 35 years, the first 20 years or so was all electronic design automation for hardware designers. We want you to design the next Pentium processors, right? The next accelerators. And on the last 10 years or 15 years, I would say we kind of shift the focus somewhat to enable software people to design integrated circuits, especially on FPGAs. So we say, why you change the focus somewhat? I would say this is just to enable what we call the customized computing. On this chart, I'll give you the reason why we were thinking about customized computing 15 years ago. So many of you see this chart originating out of Intel, basically saying if you simply do frequency scaling, and you will generate a tremendous amount of heat, although transistor can go very fast. So today you are all running at the 2 to 4 gigahertz, but we can make terahertz transistors, single transistors, not a problem, but we integrate all of them, your chip will burn. So the industry at that time, towards the sort of mid or end of 2000, take a right-hand turn. They go with parallelization, saying we more or less fix the frequency, but we add more and more cores on that. And there's you do go through analysis that will actually help with the power density and the heat dissipation. We actually proposed at that time a sort of a bold move, saying you should go one step further. You adapt your architecture to your application. Don't use a fixed processor architecture and you change that. So we were fortunate, we submitted a proposal to the National Science Foundation. We got funded by so-called Expedition in Computing Award. At that time was considered to be one of the largest awards, $10 million over 5 years. And if you see this quote that coming from our proposal, we says we want to look beyond parallelization to focus on domain specific customization, right, to achieve order of magnitude efficiency. So did we go that direction? Absolutely, yes. So in fact, there's many good examples. Probably one of the best well-known one is the Google TPUs, right, Tensor Processing Unit. It's all designed to just handle one type of workload, which is deep learning. If you actually boil it down, it's the basically building blocks there are matrix vector multiplication or matrix multiplication. At the time they published the paper, they quoted the 70x the improvement over leading edge processors and 200x over leading edge processors, 70x over GPUs. Of course, both the CPUs, GPUs, and TPUs all improved. So this number probably goes up and down somewhat. However, there's one limitation. If you want to create this kind of a chip, you should have a very deep pocket. If you follow the McKinsey, the survey to design a chip at the 7 nanometer, probably costs you $200 million. So do you have $200 million? That's number one. Number two is that you have to be patient. For example, my graduate student will hate to do that because from the time you have the idea, when you're trying to fabricate, that'll be 24 months. And you may have a bug, and come back, you have another one. So when can you graduate? You need 3 papers maybe. Here you go. So that takes too much. But not only that, as you do this, the algorithm keep refining and advancing. So maybe what you designed for is sort of obsolete. But however, there's other alternatives. You can actually do your customization on a programmable substrate where you can still achieve very high computing efficiency, but with a lot of specialization. One example I'm quoting here is for example, what we did 2 years ago, published the ICCAD'2022, very classical problem. How do you do sorting? At a very large scale, not to sort 10,000 numbers, but can you sort 10 terabyte of numbers? So the way to do that is to use this simple merge sort algorithm we have. You sort it into small chunks and keep merging them into larger chunks. You can show that's computation-wide, it's n-log-n optimal, and the data movement is also optimal. But how do you specialize? Specialize depends on how wide is your kind of I/O bandwidth, right? And how much data you have to solve. So basically there's 2 parameters, this merge tree, how many leaves you have, and what's the throughput you have at every node. If you do an ASIC design, you cannot customize it. For in our case, if you tell us I'm going to sort 1 terabyte of data, and then my record is 100 bytes, and then we can customize everything to get a dedicated merge tree for you. Not only that, you will actually find out when you want to sort let's say terabytes of data, it will not fit into memory. But how do you do it? The best way to do that is to sort it into memory-wide chunks. For example, your memory is 256 gigabytes. You sort it into 256 gigabytes, and then you merge them into a long run. But then the merging is going to take place from in the SSD. SSD has much lower bandwidth than the main memory. So during this transition from a DRAM sorting to SSD sorting, we actually reconfigured the FPGA. You get another customized circuit for that. Again, this is not something that you can do with ASIC. The customization takes about 1 second, but altogether you sort terabytes of data takes about 200 seconds. So if you look at the paper, if you compare to CPU, GPU, or the alternative or cluster of CPUs, this one has the best performance, best throughput. So basically the message is that the FPGA give you this the trade-off between the cost, performance, and throughput. I like this paper from Professor Bill Daddy's group at Stanford, basically summarized the power of customization. So how can you get this very high efficiency? One is that you use special data types. You know, in AI inferencing, a lot of time we're using 8-bit data, right? We did genomic processing. You have 4 different basic building blocks, right? The ATCG, we use 2-bit of data. And then there's massive parallelism that you do a matrix multiplication. I will show you, for example, use systolic arrays. Every element that the processing element can do some processing. It's not a 16-way parallelization. It can be hundreds of ways or thousands of ways. And you can optimize the memory. You don't have the standard L1, L2, L3 cache. You keep the data as long as you need it, and then you release that. And you reduce the amortization, you amortize the instruction overhead. In order just to do a simple add operation on a standard processor, what you need to do, you need to fetch the instruction, you need to decode it, you want to see whether the 2 operands are available or not, and then you schedule it. So there's a lot of overhead just to process one, but add, you just add, you have the adder and the 2 data comes in. So when you do customize, that's actually what you can achieve. And finally, that you can think about how do you adapt the algorithms to the architecture and vice versa. So that altogether give you this order of magnitude, multiple orders of magnitude of performance. Obviously, this is the most efficient when you go to ASIC, but I will say that you get the 4 or 5x less efficiency to FPGA, but still tremendous gain over CPUs. So I hope that gets you convinced that, well, this is very important. Maybe every programmer should be thinking about the design customized accelerators. Can they do that? Can every programmer easily design a DSA? DSA stands for domain-specific accelerator. Maybe that's too much to ask. I will say there are programmers, they just be happy to get things working, doesn't care about performance. So those ones, and I think it's rather, it's not very easy to get them to design it. But there's also serious programmers. Many of you are sitting here, when you write CAD programs, you can say, okay, does this one fit into my cache? Maybe I should tile my loops. But it's all on a software level. So for these people, I want them to design customized accelerators very easily. So that's not our goal. So as long as you know how to do some performance optimization on CPUs, I want you to be able to design circuit. So where we stand, I would say the answer is yes and no. So immediately when I talk about the design circuits automatically, and you think about high-level synthesis, and so Professor Mitra mentioned about this work we did almost 20 years ago, right, to take C, C++ all the way down, go through LVM, do the code transformation and the scheduling, resource allocation to get you the RTL. So this flow is proven, actually it's working, that Xilinx made the acquisition. And so we started with a university project called the XPilot, and later on we have the spin-off company AutoESO become Autopilot, and the Vivado HI, so Vitis HI, so about that. Before the acquisition, obviously the buyer had to do some technical due diligence. They actually did a lot of tests. Not only they did the test, they hired a company outside called the Berkeley Design Automation. They did the test. So the conclusion is that the QOR can match the output of a manual designs, writing RTL code. And all these results, by the way, and we collaborated, convinced them to publish in this Keynote paper in Transaction on CAD in 2011. So you can look for the details about the set of benchmarks being used, the performance achieved. So he says, that sounds very good, that what's the problem? So indeed, that's the good news, that it's not difficult to create a circuit from C++ input using high-level synthesis. For example, if I showed you this, one of the benchmarks examples from Polybench, right? A lot of people use that to tune the performance. So there's two loops to do matrix vector multiplication. You basically press a button and you will get an FPGA out. So we have that automated flow. However, there are challenges. This is not end of story, otherwise my keynote will end here. The challenge is that you indeed press the button, but then you measure the performance. Oh boy, that this is 13x slower than a single thread CPU. So what's the point if your design accelerator is slower than CPU? Which is not surprising. By the way, CPU typically add up 2 to the 4 gigahertz. FPGA, you'll be quite lucky to design a 300 megahertz, maybe pushing to 500. So you lose a few, the X frequency-wide automatically. But this performance slowdown is worrisome, but on the other hand, it's not uncommon, right? So have any of you written parallel programs? The first version of that most likely has no speed up. That you give it to a 16-core CPU, you don't see 16x speed up. How do you do that? You do some profiling. It says, okay, I have to give these pragmas, hints, right? To say you parallel this section, you parallel this section, and maybe you do a reduction. So that's actually what you need to do as well. So high-level synthesis give you so-called pragmas. So you add it in, for example, the pragma says for the first loop, you do pipeline. And for the second nested loop, one is that you do parallel, the other one you do parallel with a factor 16, and then you also do a reduction. So you add these 3 pragmas. Now we're back in business, we're 120x faster, right? So by doing this. By the way, this pragma may be slightly different from the what you're familiar with Vivado HS pragma, because this is actually the pragmas done using Merlin compiler, which is another spin-off we had from UCLA called Falcon Computing. Xilinx acquired that 2 years ago, but it's all open source. You can use that. Because it does a lot of automatic code transformation. So in terms of pragma, it's very simple. There's only 3 kinds of a pragma, either parallel or pipeline or tiling. So that's it's easier to use that for illustration. Now you look at it, it says, okay, this is not too bad. If you insert 3 pragmas, you can get 120x. Maybe I'll just try that, right, to figure out which 3. But this is another problem, is that if you really want to sort of look at all the possibilities. Remember I said I have 3 pragmas, right? Parallel, pipeline, tiling, but you can do it at every loop boundary. Even you have 4 or 5 loops that this is a kind of a compounded exponentially. So in this case, it's over 3 million designs, so you cannot renumerate that manually. So how do we solve that? So I will tell you kind of the approach we are taking. So in order to democratize this accelerator design, really we hope not only to stay at C, we can move to higher levels using like a TensorFlow, Halide, Spark, right? And then we'll create this intermediate layer, which we'll come back to tell you. But for this community, probably you are more interested in saying, how do we do the optimization? So we take it out into 3 parts, or 2 parts. One is that I call that we do so-called architecture-guided optimization. So if I know that a certain application can be done efficiently on certain architecture templates, so I will go with that. So some examples are systolic arrays, stencil computations, right? We also have a new class of architecture, we call it the CPPs, stands for Composable, Parallel, and Pipeline Architecture. Now for general programs, now we are still investigating, but we think it's actually possible to do it using machine learning or deep learning, which I'll get to that. Then finally, want to compose different accelerators together very efficiently. So that's kind of our overall strategy. I will going through some example to share with you what we have done. As I said, the goal is that with this kind of tools, you can let the software programmer to start at a pretty high level and go all the way to get a very efficient accelerators. So let's first talk about give you an example about architecture-specific optimization. That's called AutoSA, just mapping a set of code and normally deep learning kernels to systolic arrays. This is a classical paper back in the 70s by Professor H.T. Cong and Charles Lazarson. They first formalized this concept of systolic array. The idea is that you can have this computation that going on in a systolic manner. And so basically the data will actually go to the processing elements. They will compute and then pass on to the next one. They will compute. So this is an illustration for matrix multiplication. You have A arrays and streaming from the top, B arrays streaming from the bottom. And so why we're interested in that? Obviously, you have a lot of parallelism, right? You can have a big array that TPU, by the way, is based on systolic array, that 12 by 12 and 24 by 24. Moreover is the locality. Some of us worked on interconnect optimization for many years. In modern CPUs, what dominates the performance is not the gate speed, but the wire speed. So this has only nearest neighbor connections. So it's not surprising a lot of accelerators for deep learning was all using systolic arrays, and from Google, from Tesla, from Amazon. However, it's not so easy to design systolic, although conceptually it's quite simple. And so this is a slide coming from Intel. They showed a number of high-level designs they did with C, with OpenCL, C, or Verilog directly. 3 of them actually are systolic arrays. You can see it takes them 4 months all the way to 18 months to get not a design, but get a design with good performance. So this is something we want to automate. So this is what's the challenge? The challenge is not to get a systolic array working, but the challenge is to get the best, or maybe something close to the best to work. So I will show you the sense of a design space. For example, you can have either 1D array or 2D array. You have all possible dimensions of a systolic array you can explore. So this now we fully automated. We have this tool called AutoSA. It's all open source. I have a time to give you a few kind of highlights. That it has 2 parts. The first is start with the legality checking, whether you give me a piece of code, can that be implemented in systolic array? You have to make sure there's a constant dependency in every direction, right? So in fact, if you want only nearest neighbor connection, you should make sure that in those dimensions, you have a dependency distance equal to 1. But it actually fits a lot of applications that like a matrix multiplication, CNN kernels. Now we break it down into 2 big parts. One is the computation, the other one is the communication. Let's give you some idea about how do we do the computation management. So this is a matrix multiplication example, 3-level nested loop. So the first decision you have to make is, we call that the space-time mapping or transformation. You have to figure out which set of loops goes in a spatial dimension. You have the 2D array, for example, and which set of loops goes in 1D direction that iterate on a single processor. Right, so this, we start with a polyhedral model. We can analyze the dependency. We'll do certain necessary enumeration to find out the subset, which is the most promising subset that can give us the optimal solution. And then your data could be very large. For example, you process 1024 by 24 data. So you cannot have one element that for every matrix elements. So you have to create a physical array which much smaller than the virtual array, your data array, right? So we call that the array partitioning. you come out, basically you overlay the computation on the physical array. So which means that you have to tile, bring out a certain tile of the loops so that you can create that physical loop. So there we have some optimization I will talk about to decide what's the tile factors, right? And then life is not so simple as you do one clock's computation, shift it to your right neighbor, and then they can do another clock of a computation. A lot of operations, even like a floating point, add and multiply, takes several clock cycles. So you do it, and then you have to spend, let's say, 5 to 10 cycles to do it. Your neighbor's waiting, right? So it turned out the better way to do that is that you start something, and you take, let's say, 8 cycles to finish, but immediately I start another computation for independent data, right? So that I basically have 8 computation going on in 8 cycles, and every cycle I will ship some data to the neighbor. And it's not the same data for the same computation. So that means that you have to peel off another layer of the loop, or maybe a pair of the loops that to do, we call the latency hiding. And finally, that your PEs doesn't have to be a single the MAC multiply and the accumulator operation. It can be a SIMD engine. You can have a vector operation, right, to have processing 8 elements or 16 elements altogether. So this is the design space we'll be looking at. This is something we can all automate. You can see that's why it takes time to do that. Now you can say, okay, I got it, that you have all these options. How about the data management? Because this is key. You want to make sure you only have nearest neighbor that communication, right? You cannot, you don't want to do broadcast. The way we do that is actually to do the dependency analysis. Actually has a direct connection to data communication. You can see in this matrix multiplication example, you have read after read, the dependency for A and the B matrix. Normally in CPUs, we don't care about the read after read dependency, right? Those are harmless, but in systolic design, it's actually very important. And then you also have a so-called read after write, that because C array will be accumulated, and finally that you have different ones writing to different part of the C array. And from here, you actually have this table. You figure out that which group is doing this dependency. Then from here, it's interesting is that you can construct your network this way. For example, you have the dependency vectors, and if you find out that the vector is in the J dimension, you want to stream in your data in the J dimension. And if the dependency is in the I dimension, you are streaming the data in the I dimension. This is all through the polyhedral analysis. And then once you have this dependency analysis, I can construct that communication network this way, and I can guarantee it's correct with only nearest neighbor computation. So I will not go into the details. I'll be happy to share the paper with you. And then finally, you got to read out the data. And then I told you there's a number of parameters we have to deal with. A big part is the tiling parameter, that when you actually come out to decide what's the physical array dimension, right? So there we are using a hybrid approach. First we do mathematical programming based optimizer, and then we do evolution search. The reason we need evolution search is that I will show you the delicacy, is that you cannot just having integer divisors as the parameters, that you have to do rounding. And that's number one. Number two is that I want to emphasize the reason I separate this class, I call that microarchitecture driven optimization, is that once you define the microarchitecture template, I can estimate the performance quite accurately based on that template. So this made it possible to do mathematical programming based optimization. So I will show you some of these benchmarks results very quickly. You can see these are very large dimensions, matrix multiplication, CNN, and other numerical computations. And we can also do sort of a not only rectangular array, the LU decomposition is a triangular array, and we can handle that as well. This, I will not go into details, but if you look at our performance, with the published result, the best result at that time, that the AutoSA is consistently giving very high performance and with very high DSP utilization, close to kind of 100%. And this is all open source, and you are welcome to take the project and then enhance that, adding new features. I also have a student working on it. The Jie, the main author that has graduated, is working with Amazon, but I have a new student continuing the effort. We'll be very happy to see you use this package. So let me tell you some surprising result. Once you have such a kind of a detailed architecture exploration tool, what can we learn? If you go to, they give us a lot of architecture insight. One insight is that what's the dimension of a physical array? Should that always be an integer divisor of your data array size? For example, if I have 1024, should you only try 2, 4, right, 8, 16, and so on and so forth, being a integer divisor of 1024? Indeed, a number of papers based on that assumption to do design space exploration is published at the top places. But we actually show this is not always true. And for example, the reason is very simple. You could actually, for example, in this design, will fit the array and in one dimension, and then if you double it, it will not fit. But however, if you kind of having some fraction numbers, that's work out the best. So for this matrix multiplication example, we can show you very clearly, if you do a divisor-based approach, the best one is 32 in one dimension, 4 in another dimension, and then 8 is the SIMD size. So basically elements can do, every PE can do 8 elements operation. So that gives you 500 some gigaops operation. But if you pick some strange numbers like a 16 times 13 times 8, then we can be 50% higher performance, like a 750 gigaops operation. So that's surprising. Another surprising result is a lot of people know that the memory movement is very important off chip, right? So if you don't optimize that, most likely you cannot get the optimal solution. A lot of people just says, maybe I can just minimize the off-chip data movement, that will give me the optimal solution. So a number of papers based on that assumption. Again, we showed, no, that's not always true. So again, with the same example I was showing you earlier, if you calculate the data movement, the second one actually has slightly higher data movement. And interestingly, because this design is actually has a high computation intensity, so the computation matters. You want to make sure your computation engine is fully utilized. So it just shows some of the work that if you base on architecture simulation or something, you cannot really study this kind of details that carefully, and you may lead to wrong conclusions. So hopefully by now you says, okay, I'm convinced the systolic array you can do it well, but how about the general programs? By the way, not only we do systolic array, but something like a stencil, we can do it optimally, proven optimally, right? When both computation and communication. And there's a few classes we can do. But the challenge obviously is the general program. For example, I showed you some, so this is where we make use of this Merlin compiler I talked about. The reason we use that is just we designed it in such a way that it's very similar to OpenMP, that kind of a framework for multi-core CPUs. We think that's probably the closest the software programmer can take on. And in OpenMP, how do you parallel program? You add a program as an OMP that the parallel for, you parallelize that for loop. So here we just say program that the Excel, you do parallel, that's it. You can add a factor saying you want to do factor 16 or 32. And underneath, Merlin does a lot of transformation, because in order to do that, you have to partition your memory properly. You have to actually buffer some data and to do the host interface. So that actually all automated. So also we think that's very easy to work with. So the first approach we take is very, I would say, kind of like an expert system, right? So how do you design an accelerator? So most likely you do a design without any program. You say, so how is that? Maybe I'm lucky, I can actually hit my performance goal already. So you start with no program, and then you go to read this output report. You say, oh, there are so many cycles. And then the profile that the Meridian output is actually very detailed to show you where the contribution come from, or these cycles. Now you say, this two-level nested loop give me the most of the delay. So then you go in to add some parameters on those nested loops, right? So it's kind of a guided, I would say bottleneck guided optimization. This one actually is very effective just by these techniques. And the Xilinx, for example, publish all these HRS libraries on different, in different domains. That this domain we picked on is for vision. So they have 30, 40 kernels. So we actually pick up 33 kernels. Each one, they have 13 HRS parameters. Use these techniques, we get rid of almost all of them. All this parallel array partitioning, unroll, and we can start with program without anything. But we do need the data flow parameters, which we can take that, just pass it through. I'll come back to talk about data flow. The parameter is actually very important for the accelerator composition. But however, there's one limitation. The limitation is that for every iteration, I do have to run the high-level synthesis to know the performance breakdown. So for those of you who actually run high-level synthesis tool, it's not bad, but it can take 10 minutes, sometimes 20, sometimes 30 minutes. So in a day, how many iterations you can go through? Maybe 20, 40, right? But remember, I showed you there are millions of points in the solution space. So this is where we think that maybe deep learning can help. So we want to come up with a model that can give us prediction, right? So if the machine learning can be the best chess player, maybe it can also be the best circuit designer, right? Coming up with that. So that's what we hope. As we study, actually, we find out this is much more difficult than playing chess, because chess, although it's quite challenging, big board, but its rule is fixed. But with accelerated design, it's like writing algorithm that it's all open-ended, right? It's only limited by your creativity. So that's very large solutions. But nevertheless, we have a rather modest goal, is that give me the program, give me the parameters, can I predict the performance very accurately? So then I can iterate. Remember, by the way, the AlphaGo exciting moment for them is also that once you have the chess board, you have the black the pieces and the white pieces. Once they see that, they can come up with score function. They can do that prediction. That's the key, allow them to do machine learning. So we want to do the same. When I see the program with the parameters, I want to get a performance estimation of that. Another question is that how do I treat this program with parameters? You treat it as a string of vectors or natural language. In fact, I found out the program is very different from natural languages, because when I speak here, there's a lot of redundancy. You can skip maybe every fifth word, you can still know what I'm talking about. Program is very sensitive. If you misplace a semicolon, you get a very different result. So you cannot actually use a lot of these NLP training techniques. After some struggle, we actually decided, so by the way, just to tell you, this is a problem we want to solve, right? So we want to be able to automatically insert the parameters, and we can want to search that solution space. So first, we get to create training examples. It's good we have auto DSC, because as auto DSC was searching, we will keep not only the final result, we'll keep all the intermediate results. So these are our training examples. Not only that, because we do bottleneck-driven optimization, those are still meaningful designs, although it's not the optimal, but we also do some perturbation, so we want to include both good and bad design. So that's the way we actually create this database. So we have a few thousand. I hope you can work with us, maybe community-wide, we can produce a lot more, right? So coming back to say, how do I represent a program? That after some struggle, we decided to represent it by a graph, because the graph captures the essence of a computation. So I represented it basically as a CDFG, control and the data flow graph, because the nodes can be operands and all the operators, and they can have attributes, talk about the data type, right? The vectors that for example, bit width and so on and so forth. There's tools you can take the C programs, going through LLVM compiler, for example, and then you can construct a data flow diagram. And then we have to add all these informations about the pragma, which I will skip some details. And from this one, and there's a lot of exciting progress on graph neural networks. In fact, I noticed there's a special session at this conference right after Keynote on graph neural network. I think it's very timely. And so we will encode the graph into a multidimensional vector, or maybe multiple multidimensional vectors. So in our case, that we consider the node attention, right? We consider the knowledge jumping. So there's a number of techniques before we construct that vector. And then basically that's a graph embedding. You embed the graph in a high dimensional space, and then you do decoding. From there, we can get the performance out. So then with this, then it's much faster. I don't have to run high-level synthesis tool. We can do the design space exploration. I will pick the, in our first version, just do enumeration. We can pick the top M designs. And then from those M designs, I do high-level synthesis. So what I'm happy to report is that now we are fairly happy with the accuracy that in terms of the mean square errors. And as we improve the tool, that you may actually get the inaccurate result, but you can always add it back to the database, keep training that. Then we tried it on some of these unseen kernels. We actually get quite a good result in compared to AutoDSC, which we let it run for the whole day. Here, we just limited, for example, to 1 hour. We get the comparable, in many cases, better result. However, it's not the end of the story. We still struggle a little bit if I give some result examples very different from everything we have in a training set. So that's called the out-of-domain distribution. So this is where we want to leverage this concept called transfer learning. So the idea is that if you give me something brand new that I'm going to build a model, I have to run 1 or 2 or 3 high-level synthesis on some samples, and then I update my model, and then to kind of use that to do exploration. So this is all inspired by this so-called K-short image classification in the machine learning field, right? So the early the classification tool is that I learn from 1 million images. I can tell 1,000 category, dog and a cat and something. So now there's also that if I give you a new animal, camel, for example, you have never seen, can you recognize that? The idea is that obviously I have to teach you something, but maybe with 2 or 3 pictures of a camel, then you can know, oh, this is camel. You can tell that consistently later on. The way to organize it is that you want to train differently. You will have a few animals, each one with a few examples on each one of them. Each of this is called a task. You want to do well on all these tasks. Basically, each task is small number of examples, and you want to distinguish among these tasks. So what's going on mathematically is that you iterate through all these tasks, right? You do gradient descent. Every task gives you a new gradient, and then you do some kind of a weighted average. You make progress. And then at the inferencing time, when you see a new task, basically a new animal, or in our case, a new program, then you will run a few times, and then you will kind of minimize the error. So give you another gradient, and then you use this gradient to update whatever the model you have. So this is the adaptation part. So with that, actually, we get a more robust result. It's better than just simple fine-tuning. I will say that we still have some way to go, especially on resource management part, because there's a few cases we get a fantastic result, but then it goes over the resources we have. So that we have to deal with more precisely. But nevertheless, AutoDSC and the GNN-DSC are also open source. So you should, if you are interested to continue on this line of work, you're welcome to download it. So now you say, you have something with microarchitecture driven optimization, some of these learning-based techniques. How do you integrate everything together? So this is something I want to talk a little bit about this intermediate level using HydroCL or MLIR. So that actually will give us the leads to the optimization I talk later on. The HydroCL work is jointly together with Professor Zhu Zhang at Cornell. Unfortunately, Zhu cannot be here. So it's all inspired by halide. Some of you may know this language, halide, for image processing. It's quite exciting. It's, I would say, within 10 years, it's being widely adopted. Conceptually, it's very simple. You write your program, define the functionality of the program. There's no pragmas in that program. However, you have a separate section called the scheduling section, which is also, you can think about the optimization section. You say, I'm going to apply on roll, and I'm going to apply some different optimization to this program. So think about it, you have the almost like a data, and then you have the operator, right, on that semantics. So it's very successful. And then we extend that for hardware designs, for accelerator design. So there's 3 kinds of optimization we can say. One is that specialized compute. For example, we can define that the on-roll being some of the loop. The other one is a data type that was not in the original halide. You can easily say, I want to try from 2 bits to 16-bit, what kind of a result we have. And we can also specify that some data reuse, you can give influence about that. So, and then that was in the original halide, and very quickly we realized we can give people the freedom to say this section code, I want to do systolic rate, this one I want to do stencil. Because that just by computation pattern has nothing to do with your BRAM, URAM, all of those. A software designer can totally handle that. For the ones you do not handle, and then we'll do automatic synthesis with auto DSC or machine learning based techniques. So finally, before I end, I want to touch one more question. That's just about how do you put everything together? For some of you who do real FPGA design, when you put everything together, boy, that performance really dropped. It's from like 300 megahertz, probably down to 100 megahertz. And also it takes so long to generate the bit stream. And 20 hours is not the exaggeration, and 40 hours, totally possible, right? It turned out that that's one area we made excellent progress recently. By the way, you don't have to feel bad that you did anything wrong to get a lower performance. It's just FPGA, the large FPGA is very complex. For example, did you realize that it has all these, the large FPGA has 4 dies, not the one FPGA, right? They have 4 dies on the silicon substrate. So if you ever goes across this die, then that's very bad. The delay jumped, right, from a few nanoseconds goes to tens of nanoseconds. And then also they have a lot of IPs being there to obstruct a lot of place and route operation. For example, you have the DDR memory that right, the controllers in the middle, and then you have the PCIe controllers at the end to talk to the CPUs. And some of these latest FPGA has HBMs. The HBM has 32 channels. And then how do you connect to your data? You need to create some kind of a gigantic crossbar. So that crossbar may take one big percentage of your chip. So with all of this, so no wonder you are actually getting a poor performance. So, and then the HRS has a limited consideration of this. When you write your C code with pragmas, you do not know where you will cross the die boundary, where you'll run into these IP blocks. So now our approach is actually quite simple. So if you have a long wire, I can actually cross that in multiple clock cycles, basically by inserting pipelines in a pipeline stage, in the long wires, right? So the question is, where is the long wire? So that's where we'll do a floor plan design that first, that the course level floor plan design to use that to guide the global optimization. And it's actually ideal to start from high level synthesis because I start with a kind of a abstract representation. I have the freedom to do scheduling. If I need 2 extra clock cycles, I can add it to my scheduling solution. So that's actually where we had a lot of success. Consistently now we see almost like a 2x improvement, for example, from 150 megahertz to 297. This is over 43 designs. I can tell you every single project in my lab use this auto bridge. This is the best paper award at FPGA 21. And just because students naturally get this 2x performance advantages over that. So if you should share with your group. Not only that, for example, I can show you this design, talk about a systolic array. You go from 12 by 12 array all the way to 24 by 24 array. You can see performance dropped. And in a conventional case, goes from 30 megahertz down to 150 or 120. But with auto bridge, we'll more or less maintain constant. So you can see on the right-hand side, that's the mysterious part. On the left-hand side, the place and route tool seems to do a good job. They pack everything right in as few as dies as possible, but they create a lot of congestions. So we can feel comfortable to separate it out, and then we insert pipeline registers as needed. It turned out these techniques, I call that the latency insensitive designs, because you can tolerate this long latency, can help us to improve place and route time as well. If you run Xilinx tool, you say it's so slow, 40 hours, and you profile your CPU usage, well, you only use 4 cores. You say, I have a 32 cores. Why is now using 32 cores? Because you cannot optimize circuit piece by piece, because there's a global interconnect, right? With this methodology, remember, we add the flip-flops at the boundary, so it's totally decoupled each component, so we can run them in parallel. So this is actually an amazing result that, in a sense, we can get the 5 to 10x speed up, and we also get the 2x. That not, in this case, not 2x on this set of example, but a 30% frequency improvement. So we have a slight extension of a HLS called TAPA. Basically, we add some templates to describe this data flow design. From there, we can automatically do this latency incentive optimization. For example, in our group, we have this FlexCNN that all designed using that, and with 14,000 line of code, and so this is all using latency incentive design. So finally, I'd like to conclude. I know time is quite short, but I'm rather encouraged by the progress that in this direction to democratize the customized computing. Maybe I'm a little bit biased. I chose more of a research done in my group, but there's a community-wide effort doing that. And it does take a community-wide effort. That's why it's so important we emphasize on our tools are open source. I hope that many of you sitting in the audience will add to that, right? And the industry is going that direction as well, a little bit more open. For example, the one API from Intel is open source. And I told you, right, that the Merlin compiler is open source by AMD Xilinx with some encouragement from us. We are increasingly interested in using MLIR as a focal point to integrate some of these efforts. So that many of you probably listened to this talk by Hennessy and Patterson in their Turing Award lecture. So this is a golden age for computer architects, which is absolutely true, because it used to be the case you only have microprocessors and controllers, a few type of things you design. Now with all these possible accelerators, and there's unlimited, unbounded opportunities. However, my message is that don't make it just a fund for hardware architects. I wanted all the software programmers to be able to participate. They can design his or her own accelerators, either on-premise or in the cloud, right? And I hope many of you will join this journey to make this an exciting field. However, if I end the talk here, I know my former advisor will be unhappy because I didn't tell any story, so I have to tell you one very quickly. Some of you know that I'm actually taking this semester sabbatical at Harvard University. I'm actually visiting physics department. My host is Professor Misha Lukin, and also together with Professor H.T. Cong, and the inventor of systology in engineering. So the first week, you're just trying to get oriented to figure out where to eat, right? So I ran into this place called HLS Cafe. I was very excited. I said, wow, And I walked up and noticed there actually is a big hall that maybe not all these people, at least half these people, there's people standing in line to get food. I said, I didn't know there are so many people designing HLIs at Harvard. So I was in line and behind this young lady, I asked her, says, does everyone here do HL's design? She looked at me a little bit puzzled. She said, I'm not sure what you mean, but we are all from Harvard Law School. Yeah. So with that, I want to thank all my collaborators and the funding agencies, and obviously this is an effort with many generations of the students, the postdocs, and visiting researchers. Thank you so much again for this wonderful opportunity.
Thank you so much for that inspiring and insightful talk. We have time for just few questions. Yes, Rakesh, please go ahead.
There's a mic there.
Rakesh Kumar, University of Illinois. I understand the argument for customizable computing. I'm trying to wrap my head around the argument for democratizing design. Can you talk a little bit about the compelling scenarios where democratization has had success or will have success? Because when I think about this, most successful commercial hardware is still coming out of companies that have those $200 million that they can devote to having custom designers build hardware. So where do you see the biggest benefits of democratizing design?
Yeah, so I think the potential, the opportunity is absolutely there. For example, Amazon, if you use Amazon, they charge you money, but more important, they charge you storage, right? So if you know you have some data, you don't need it, and you can just compress it, and in many cases 10x, 20x, and then you store it. So that compression takes computation resource. Do you use it for CPU, or do you use it for accelerator? Accelerator will be a lot more efficient, you do it that way. But most of the software people, they have no idea how to design an accelerator to do compression. They would just use CPU to do compression, right? So my former student, Professor Pepe Zhou, is sitting there. She actually did a lot of just talking about the cost, right? The study. You run genomic sequencing, and the most compute-intensive part is to do this BWA algorithm. That's actually, in many cases, in early days, takes many, many hours. So we can accelerate it using that a few minutes, right? So then the question is that FPGA does cost 4 times more expensive than CPU instances. Should you use that or not? So, but a lot of people has no idea how to create this kind of accelerator. We are the ones created, and the UCLA Medical School is using that. But I can show you slides who have done this for different areas, like medical application, big data, like sorting. And we work with neuroscience for neuroconstruction. We'll be happy to do this collaboration, but at some point, I really hope they can take over to create their own accelerators, right? So I'll have another cool project that, for example, we have just to understand AI, really you have to understand how nature works. So we actually work with neuroscientists. We have this calcium imaging on the head of a rat. And when you think that the neuron fires, and you can actually see the firing with calcium imaging, that need to be processed real time. And then, so that's actually on FPGA. And then the goal is to provide feedbacks as well. For example, for patient with seizures, you may actually want to interfere, ask him or her to pull out, right, the highway, if that's a signal that getting into kind of a dangerous condition. So all these things that you need this customized accelerator. Right now, the neuroscientist people, they cannot design. I'm working on quantum computing. You need actually accelerator to control the quantum computer. That's actually done by FPGAs. Again, they are learning high-level synthesis that you'll be surprised that, to create these accelerators.
Thank you, and thank you for the great talk.
Thank you. Okay, I think we are really short of time, but Professor Kong is going to be here. So if you can ask him the questions during the break. And we have a very small token of appreciation.
Oh, okay, great.